Welcome to the 16th video from the playlist Leetcode Top Interview 150 questions. In this video, we will be solving the 16th problem from the Leetcode Top Interview 150 list. The name of the problem is trapping rainwater. In this question, it is being asked, we are given n non-negative integers representing an elevation map like this, where the width of each bar is 1, and we have to compute how much water it can trap after raining. So if it rains from the top, you see the blue part of this is the water which can be trapped between these elevations. Now in this case, this is the height given. We have 0 height, 1, 0 height again, height of 2, 1, 0 again, 1, 3, 2, 1, 2 and 1. Now you can see at the edges we cannot store any water because it will just flow down from the corners. Now for this question the output is 6 because we have 1 unit of water here, 1 unit of water here, total 2. We have 1 unit of water here and 3 units of water here. So let's take a look at how we can solve this problem. So let's take this input array and see that what we can do to solve this problem. So by looking at the picture, we are noticing that the water can only stay between two verticals which are of height greater than 0, and the height of the water is bounded by the minimum of the either the left vertical or the right vertical. So here in this case, if you see that at index 3 the height is 2 and at index 7 the height is 3. So in this case the height of the water was bounded by the height 2, because any water if you try to store in this range will flow down from the left hand side. So we always know that the height of the water is bounded by the minimum of the height which we have from the left boundary or the right boundary. So that's for sure. Now to be able to calculate the water accumulation at every index, what we need is the maximum height from left side boundary for each index, and we need the maximum height from right side boundary for each index. So if we have to calculate that, what we can do is we can take a max height from left, and then what we can do is for every index we can calculate what is the max height we have seen so far. So the maximum we have seen so far is 0 from the left hand side. The maximum, now we have a new max called 1, so the max would be 1. We have the current element is again 0, so now the max is still 1. We have current element is 2, so the max becomes 2. We have current element as 1, but we have max as still 2 from left. We keep going there. Current element is 0, max is still 2. Current element is 1, max is still 1, max is still 2. And then we have current element as 3, and we update the max to 3. And then this will continue to be the max when we are looking at from the left hand side. So if we calculate this array, which is maximum height from left hand side, we know that for every given index, what is the height of the bar on the left hand side which is the largest. Because in this picture, you know, right, for let's say for this particular range, do we care about any height which is shorter than 2 on the left hand side? No, because 2 is the height at which this water will be bounded. Let's suppose this 2 was not the max height on the left, but this vertical, instead of having value 1, this had value 4. Then in that case we could have stored more water in the because of this vertical which is higher than 2. So that's why we need to know the max height from the left hand side. Similarly, if we want to calculate the water accumulation, we also need the max height from right hand side. So let's also calculate max height from right hand side. Now this will be storing the same way, but here what we will do is, instead of starting from the left hand side, we have to start from the right hand side. So current element is 1, so max at right is 1. Then we have current element as 2, so we update the new max to 2 from right. We have the current element as 1, max from right is still 2. We have the current element as 2, max is still 2. We have current element as 3, the max becomes 3. We have current element the 1, and the max will continue to be 3 from the right hand side for all the elements here, because 3 is the maximum element for any given element in this part of the array. So for this element also, the maximum on the right hand side is 3. So I'm just going to fill 3 here to save some time. Now once we know for every given elevation or height what is the maximum value of height on the vertical from the left hand side and the right hand side, if we can subtract the value of the current elevation from minimum of whatever the height we get from the left or the right. Look, let's say this, for example, in this case, we have the max height from right as 3 and the max height from left as 2. Now, if we are at this elevation, which is 0, so this is bounded by the minimum of whatever we are finding the maximum from both left and right. So the minimum from both left and right is 2. And then we subtract the current height from 2, which is 0. So we get 2 units of water at this position. Similarly, for this position, we again have on the right maximum as 3, and from the left the maximum is 2. So we take minimum of both of them because this will be bounded by the minimum. The minimum is 2, and then we subtract it with the current height, which is 1 for this position, and then 2 minus 1 is 1 unit of water here. So if we want to calculate water accumulation, so water of I would be minimum of max height from left and max height from right minus elevation of I. So if we can apply this formula to our this height, because we already have the max height from this, and we also have the elevation. So let's just call it, instead of elevation, let's just call it height. So if we want to calculate water, then in this case, what is the minimum value from 3 and 0? It is 0. So we take 0 and then we do minus and then we do height. What is the height? 0. So the water will be 0 here. Then again we have to do a minimum. So minimum of 3 and 1 is 1. We subtract it with height, it will be again 0. Then again we have to take a minimum of 1 and 3, so it is 1, and then we subtract 0 from 1, so we have water as 1 unit. Again we have to take a minimum of 2 and 3, so here minimum would be 2, and if we subtract 2 from the height using this formula, this will be 0. Again we have to take a minimum from 3 and 2, so 2 is minimum, and we subtract 1 from the minimum of both, so it will be 1 unit of water here. Again we have to take a minimum, so between 2 and 3 the minimum is 2, and if we subtract the current height from the minimum, it will be 2 units of water at this position. Again we calculate the minimum from both of these, so it's still 2. If we subtract the current height, we get a unit, 1 unit of water at this position. Again the minimum from both these positions, at this position the minimum of both heights would be 3, and 3 minus 3 would be 0, so no unit of water accumulated here. You can see this does not have any water at this position. Again we have to take a minimum, v2, it is 2, and 2 minus 2 would be again 0. Again we have to take a minimum, 3 2, so 3 2, the minimum of 3 and 2 would be 2. We subtract 1 from this, and then we get 1 unit of water over here. Again we have to take a minimum, so 3 and 2, the minimum is 2, we subtract 2 from 2, this will be 0. And then we have to again take a minimum for the last one, the minimum is 1, and here again we won't be able to store any unit of water. Finally, if we sum all the units, so 1 plus 1 plus 2 plus 1 plus 1, we get the answer 6. So the time complexity for this approach would be linear, but the space complexity of this approach is 3n. So now, is there a better way to solve this? So one of the better ways is that we can use a two-pointer approach, but the idea here is, instead of trying to calculate the result for the indexes in a linear sequential order, what we can do is we can calculate it at from the beginning or from the end, depending on whichever height is minimum. So let me tell you why this approach works. If you take a look at the formula, for every index, if we want to calculate the water accumulation, we need three things. We need the max height from left hand side, the max height from right hand side, and the height. Now in this formula, we always know what is the current height, which is given by the input only. If we are iterating, let's say linearly, we definitely know at least one of these values. Either if you are iterating from the left hand side, then we know the max height from left. If you are iterating from the right hand side, then we know the max height from right all the time. And we also have access to this one. The only catch is, if you fix iteration from one specific side, let's say you pick left side and then you are starting to iterate, then you will have this value, you will have this value, but you won't have this value. Because of that, you won't be able to calculate what is the water accumulation at index I. So now let's take a look at this. Do we really care about if we have max height from right at a particular index? Now the key thing to notice here is that since we are taking a minimum of max height from left or max height from right, let's say the max height from left is currently 0 or 1. So since we are taking a minimum here, it does not matter what is the max height we receive from the right hand side, because any height which is greater than 1 or 1, if the max height from left is 1, any height which we receive from the right hand side which is greater than 1 will automatically be ignored. So this formula, if we are calculating the water accumulation at a current index and we know the max height from left, then we don't need to calculate the max height from right, or we don't have to wait for the max height from right, because we know that if at this position the max height was already greater than what the max height from left is, then we don't care about that value. Now the other case is where the max height from right is smaller than the max height from left. So instead of just iterating from one hand side, which is from left to right, if we can iterate from both sides. So we are iterating from both sides, which means we are having a left pointer over here and having a right pointer over here. And if we iterate from both sides together, so in the case where we know that the height from the left hand side is smaller than height from the right hand side, then at that point we don't care about the max height from right, because we know that whatever height we will get from right will always be greater, and then we are safe to use the max height from left. Similarly, if I reach a position where the height from left hand side is greater than the height from right hand side, then we don't care the max height from left in that case, and it's safe to calculate the water accumulation at the right side. Then instead of computing the water accumulation on the left side, we compute the water accumulation on the right side, and then we similarly move our pointers, the left pointer forward and the right pointer backward. If we compute in this way, then we don't need these arrays to be stored, because at every point we will have the access from max height from left or max height from right, and we would know what to do with these. So let's try to write code for this approach and see if we can solve this problem or not. So I'm just going to copy this over here. And since we will be solving this problem by two-pointer approach, let me declare a left pointer and a right pointer. Since we have to return the total accumulation of water in the elevation map, let's create a variable to store that and a variable to store the current height. Now, while our left pointer is less than equal to our right pointer, what we discussed over here is if the height from left hand side is smaller than the height from right hand side, which means we can compute the water accumulation from left part. So if height from left hand side is less than height from right hand side, compute water accumulation for left part, else compute water accumulation from right part. So to be able to do that, this condition is the min part, because whatever we are picking as min, so whatever is smaller, we are calculating the water accumulation from that part. Now if we are picking, if the height from left hand side is smaller than height from right hand side, then in order to compute the water accumulation for left part, we need a max height from left side. So let's compute that. So in order to calculate the max height from left side, what we can do is we can maintain a current height variable, and we can just use the same process we were doing here to maintain a max height from left. So every time we see a height from left, we try to compare it with the last height, and if it is greater, then we update our max height from left. Then to calculate water contained or water accumulated, we have to subtract the current elevation, which is the height of left, from the max height from left, and then once we are done, we increase the left pointer. Similarly, we can do the same thing for the right hand side. So in this way, the current height would be something which we have seen from the right hand side, or which we have seen which is already greater than that. So this will be current height or max height from right part. Then we can calculate the water accumulation similarly, and instead of left, we can update right here, and we can shift the right pointers backward. Finally, we can return the water content. So this should be the code for this solution. Let's try to go ahead and submit this and see if we can pass the test cases. We are able to pass all the test cases, so let's try to go ahead and try to submit this and see if we can get an accepted solution. We are able to get an accepted solution. So this is how we'll be solving the problem trapping rainwater. The tricky part for this problem is converting the max height from left and converting the max height from right into a two-pointer based approach, where the reason why we don't need the max height from both sides at a given point is that we are only calculating the minimum first. So if the height from left is smaller than height of right, we don't need the max height from the other side, because since we are always taking a minimum, it does not matter what is the max height from the other side. So I hope you were able to understand this problem, and in the next video we will be solving the 17th problem from the top interview 150 list.